Okay, this talk is the last talk of this class. So in this video clip, I'm gonna explain kernel method, which is very classical method, but also useful approach to explain deep learning approaches very recently. Okay, so I believe this is very useful for your machine learning research and other things. So consider very simple machine learning algorithm called linear regression. So linear regression is, I believe, the most simplest form of function. So consider this scenario when you have n number of training data point with regression task. So which means we have an input feature xi having d-dimensional value as input, and the output is a real value y. So here yi. So essentially, we have to design some function f that can predict corresponding output yi. Okay, so let x is the matrix, which will be m by d by m. Sorry, it should be d by m, d by n. Sorry, and each columns comes from the data point input xi. So i's column is equal to xi, that is x matrix, and y is let's say vector, which is n-dimensional vector, and each element comes from the output label yi. So ith element of y vector is yi. So this is very useful notation for the remaining class. So basically, regression task, we have to find function f, function of input x, so that this fx output can predict the true label y. Usually we use square error because the square have very nice property to measure the error between fx and y, because this is always positive, and which is value 0 if and only if fx equal to y, and also it is differentiable. Also, as the absolute value fx minus y increase, this loss function also increase. So we usually use this loss function. So basically, from this we can define this objective function, sum from I1 to n, fwxi minus yi square. That is very nice objective function. Alright, good. And also, another very interesting point is the function f can be parameterized with w. So the shape of function can be controlled by w. And the main task of this regression machine learning problem is we want to find w parameter that minimize this objective function, that minimize this mean squared error, that minimize this L2 loss. Okay, and here the linear regression consider the most simplest form of linear function. So basically, the fwx is equal to x transpose w. Okay, so we have to define d parameters. So w is d-dimensional vector. So when we have x as input, then the expected output or our predicted output is just inner product between input x and the parameter w. And we have to find nice w that minimize this objective function. And usually, we also have regularizer that prevent overfitting and that improves some generalization property. So here generalization means the difference between the training error and the test error. When the number of parameter is very high, for instance, D is very high, like a million, and when the N is smaller than the D, so for instance, when we have 100 data points, but each X have millions of dimension feature, then we need to define millions of parameters, W, because we want to make a linear function, and the linear function have to have the same number of elements of W with input dimension. And in that case, there are infinitely many solutions for this simple mean squared error. Indeed, there are always perfect solution, and the number of solution is millions or billions, infinitely many. And in that case, overfitting is very crucial issue. So here overfitting means the function f(w(x) will fit the training data point. So we can explain every x and y pair using this linear function just for the training data point. But for a new sample, for a new input point, the predicted output can be very far from the true y. So for the test example, our prediction can be very bad. Because there are a bunch of solutions, there could be nice solution area, but there are also many very bad solution area. Okay? Right. So this additional Lagrangian can be one of one of solution for the overfitting issue. So this is the kind of thing. So here, rigid regression, we add lambda times of W2 square, which means we penalize the parameter growth high. So which penalize the situation. W has this kind of element value distribution. Some element has very small value, some element has very high value, some element has very small value, and so on. After with this regularization, usually the parameter space having similar value range. It is because the square shape, the slope of this square function is very small for this area, but the slope grows rapidly as the point W element point move away from the zero origin. Because of this property, when we have this kind of W vector, this element has very huge additional cost function. So when we minimize this objective function, the gradient descent or whatever optimization technique try to reduce this element but increase this element. Because when you look at the function shape of this additional cost function, almost zero slope but a very high slope here. So it is okay to increase this element, but it is not okay to increase this element. So with this additional regularization, the solution is defined uniquely, and this is the solution. W star is equal to XX transpose plus lambda ID inverse and X times Y, X matrix times Y. Okay. So to compute this solution, we need to compute the empirical covariance matrix of input X and the identity matrix, and we have to find out the inverse of this. And this is our X input matrix, and this is our output vector for the training set. We can change the W star equation like this. we can represent W star as follows. W star is equal to X times X transpose X plus lambda IN inverse of Y. So here the main difference is X transpose is changed to X transpose X. Then what is the meaning of X transpose X? This is kind of kernel. This is called kernel. This is the correlation between input data point. So this matrix is n by n matrix, and every element comes from inner product between two different input vector. Okay. So with this W star, the function FW star X is defined as follow: input X transpose, input matrix X transpose X plus lambda identity matrix inverse Y. And when you compute this, very interesting thing is every computations consists of inner product between Xi and Xj. We just need to know inner product between every pair. Even this part also, we just need to know inner product between the new input and the existing input. Okay, we don't care which X vectors we received. We don't need to know the exact vector values from x1 to xn and new input x. It is okay to know the entire inner product between two inputs. Then without information on the exact xi vectors, we can estimate fw star x. Okay? Important thing is we don't need to know the exact x vector. Instead, we can estimate fw star x from the inner product between xi and z, between all pairs, and xn, xi. Then from the values, from the inner product values, we can estimate fw star x. Okay? So I will explain why this is very useful technique.